Welcome back to another video, and we're back with the 12 volt high power test bench. I've been working on this for over a week now. I have pretty much revamped it from the ground up. I've taken some of your feedback on board that I could implement into this and made sense. Most of these changes were born out of necessity and what we have learned so far. There's a lot of things that became apparent, a lot of areas that needed to really step up in order to remove as many variables as possible, remove a lot of equipment that's floating around on the bench, stop using current clamps, and get the best data consistently and over a good period of time, which I think is going to give us a much better idea of what this 12 volt high power connector can and can't do in regards to its durability and its specifications. So let's dive in. I'll give you a quick tour around everything and show you what has changed. Right, so starting at the power supply side, everyone may have noticed that we've grown by one. I decided to add one more of these power supplies in while I can still get them and they're cheap. I've modified all of them. So we have 4 by 750 watts, which is 3,000 watts at 12 volts or around 240 amps of available power. I don't plan to use all of it. It gives us more overhead. It means I don't have to stress these out as much, and the voltage drop should be less also and should be able to keep it pretty solid around that 12 volt mark. I also made a hood. This is probably the biggest 3D print I've ever done on the Snapmaker. Came out really well, so I took your feedback on board about that and added a hood just to block the airflow of the fans. And now the airflow is going to go in here and send it out there, and that should help keep the airflow clear of this area and keep a few people happy. Now, this is where the business is. A lot of work went into this. I cannot stress this enough. Everyone's been asking, nagging me, where's the next video? So we have 6 current shunts here. They are all connected to some data logging equipment that is hiding up the back there. So we have individual current monitoring on every wire that will be going to the connector down to ridiculously accurate levels. No more current clamps, no more multimeters. It should be all automated. It'll be logged. It's going to be amazing. So the reason why I am not going to use current clamps anymore is after a lot of testing with a few different versions. Yes, they work. Yes, they're in the ballpark and you can get an idea, but there are 2 major problems. One, the accuracy of these can be out by quite a large margin and they cannot be trusted for any sort of scientific or moderately accurate measurements. So we can't do that. And the other issue is when you go to clamp the wires and you're moving things around, that affects the pin contacts on the connector, and the readings will move as you touch the wires to try and take measurements. So I want this setup to be completely hands-off. I want automated data logging that is going to do everything over a period of time, and I can just come back at the end and pull all the data and compare it to previous runs. So yeah, these shunts are very capable. They are very accurate. I have spent multiple days tweaking them, getting them as fine-tuned as possible. I took a pool of them. I picked the best ones that were closely matched that just get this thing really, really consistent. I've just got some temporary wire here at the moment, and so I can give you some demos before we switch over to a connector. And yeah, still running the 12 gauge wires here. It does not matter, like anything here, don't worry about it. It does not affect the results. The bus bars are staying. I've moved them further away. We're going to be using longer wires. I mean, the bus bar here doesn't play into it because it's going into the shunts now, but these ones will still be present, but the wire length will be much longer. But for this specific testing, it's not going to play into it anyway because we're looking at the durability of the connector, not its temperature and other things. We've still got the 4 loads, not changing that for a while. I may add more in the future. I hope not, because I'm sick of buying these things. They are really good, but I don't really want any more of them. Added a large aluminium plate here, just in case we get any burning action, and I'm not going to be around for some of this testing because it's going to be over a longer period of time. And yeah, I just wanted to add a bit more protection to this whole setup. All the data logging is up here with all the wiring running to the unit. I'll show you all that on the computer in a second, and it will be all captured on a computer that's just hanging over here. I'm not going to be showing what is in there and how I've done everything because I think I'm entitled to keep some secrets, especially with other YouTubers circling around now.
What could go wrong?
But yeah, this is what the setup is, and now let me show you what it can do. Right, so this is the data logging software, and I thought I'd just show you everything that I've got access to and how all this works. This is what took the bulk of the work, doing a lot of mental gymnastics, figuring out how to program this thing. I've created a test scenario where one wire is not performing on par with the rest, just to show you how that would display in this software. So we have individual current sensing for each wire. So this is real time at the moment. I've got a 15 amp load on the whole setup. So you can see this wire is only pulling like 637 milliamps. Because that is deficient, those wires are picking up the slack. The total current is always displayed. So we're demanding 15 amps at the loads at the moment, which is what we've got here. It also automatically calculates how much current should be going across each wire for the current load. So it should be 2.5 amps. We can see all the wires are above that because that wire isn't pulling its weight. And if I go and reconnect that wire properly, they'll all fall back into line again. Total power consumption, which is reflected at the load as well. So that's accurate there. We have voltage drop across the wires to the connector, and we have total voltage drop to the load banks. And this bit took a long time to work out, and this is showing the current loading for each wire when they're loaded down. So all these wires should be sitting at 100% if they're all performing accurately. Real world, obviously, they're not going to always be 100%. It might be 98, 102, 99, blah, blah, blah. They should be in the ballpark. But you can see that one wire that's not connected properly, that's at only doing 29% of its work, and all the others have had to pick up that slack, and we can see those percentages divvied up across its partnering wires. That's really good stuff to see in real time because I know what's happening with the current distribution across all the wires on the connector. If I need to do anything, I don't need to do any calculations later. It's all done for me already in real time. So we have all the graphing here, which is really handy also. And this is just showing, I've only got the percentages turned on at the moment, just so you can see what's happening there. Basically, this is tracking all the wires, seeing how they're performing. And these little blips here are when I've turned up the current. So I've gone from like 6 amps to 10 amps to 15 amps, and you can see all the wires diverge, and then they all come back together again once they settle down and equalize. And here just gives you an idea of what I'm actually doing. So that wire that is underperforming, I disconnected it completely, so it drops to 0%, and you see all the other wires increase to compensate. And then I reconnected this wire like all the others, and you can see they all fell back into a nice tight group again. And then I disconnected it again and it fell down, and then I partially reconnected it and put it back, and then it all came back again. So all this data is logged for as long as I wanted to do it. And as I do the durability testing on the connector, it'll be doing like prolonged stress tests, and all this data will be logged. We get minimum, maximum averages over hours. I don't need to do what other YouTubers have been doing where they just put a current clamp around a wire and take a split-second measurement, which tells you absolutely nothing about how the connector is actually performing over different current ranges and everything. So the general idea is I will run a test routine, which I'm still working on. It'll run through that, and then it will give me average, minimum, maximum numbers across that entire testing period, and I'll try to keep that consistent once I've got it worked out. So we have a baseline going forward. Hope all this makes sense. I know it's a lot of information, but I thought I should just show you the sheer amount of detail that is available here versus just using one current clamp on a wire at a time, which is just, honestly, I don't think it's worthwhile. So I just want to show you one more thing before I completely disconnect all these test wires and we switch over to a proper connector. This whole setup, like redoing this, has given me a lot more respect for what the connector is dealing with, and getting even current flow across 6 independent wires evenly every single time is not an easy task. and it takes a very small amount of resistance change for current to jump across to other wires. A lot of people have heard the saying that electricity will always take the path of least resistance. That's fine, and it's just words, but to actually see it, I don't know, it just carries a lot more weight. So you can see at the moment on the overlay, we've got 100% across all the wires. Everything is looking good. So that's with all my test wires. So if I disconnect one of the wires, we can see that that's dropped off now, and all the current is going across the other wires. So what I'm going to do is connect up this test wire that I made, which has got a couple of resistors in line. So 30% current going over this wire now, and that's it. This resistor bank that I've put on, that is 0.05 ohms. That's it. And that's enough for 70% of the current to jump across to the other wires. It's pretty wild. Like, it's not a massive change, but yeah, it's enough to have a dramatic impact on how all this operates. And this is the fresh setup. I've got a brand new PCB, brand new connectors, brand new wiring, 16 gauge on both sides now. I've just got a test load running, which you can see on the data overlay, about 300 watts roughly. So this is where it all begins in the durability testing. Everything is new. This connector's only been plugged in this one time, so we have no previous history with either of them, and we're not using something that's already done a bit of work. Right, so closing this video out, I know everyone wanted to see some real results, but baby steps, everyone. This was a lot of work. It took me a long time to get to this point, and we will be doing a lot of testing and going down a lot of rabbit holes very soon. Please, if you can show some support, help grow my channel, share, like, whatever. Like I said, I don't normally say this sort of stuff, but this data logging equipment was expensive. I didn't need it for anything other than these videos, and I need to see some sort of recouping of these costs to keep going down these rabbit holes over and over again. And I appreciate your support and all the new subscribers. Just to cover off some loose ends, and I've had a few questions in videos around recent videos from other YouTubers. This is like a fluid thing. It's changing from week to week to week. I just have to say that I feel like it's very trendy to just bag on NVIDIA over and over again. And I get that. They're a big company, blah, blah, blah. My just sort of opinion at the moment, I don't really think they're at fault with this. And I know that's like devil's advocate, hot take stuff, but you need to keep in mind they make graphics cards, and all they're concerned about is getting power to the PCB, and the wiring, the cables, connectors, everything is not really their responsibility at the end of the day. I need to be clear just about what I'm saying here is that load balancing the current over these wires should be done at the power supply side, and the power supply and the wiring is responsible for that getting to the graphics card in a way that's consistent, safe, reliable, things like that. NVIDIA just took this connector as part of the ATEX specification, and they adopted it and used it in their graphics cards. They're not really responsible for wiring a power supply, not load balancing correctly. And I have to give credit, I think, to Asus with their Astral cards with the current sensing on the pins of the connector. I think that's great, and how it ties back to their power supply, and the power supply is doing the heavy lifting around current balancing, which is where it should be. It should be done at the power supply where the power is generated and divvied up to all the connectors, and that's where all the big switching and everything is happening, and it makes much more sense to do it at that end of the chain, not at the graphics card, which is sort of just the customer. That the power supply is the supplier, graphics card is sort of the customer. It just wants clean power. It gets dumped into a single 12-volt bus, and that's it. I do agree that it should have current sensing on each pin on the graphics card, but I don't think it's the graphics card responsibility technically to load balance all these wires. That's just my opinion. Take of it what you will. Now, just in regard to some other videos, I saw the Linus video with the 5090, which, look, I don't like to bag on other people, but I don't get it, to be honest. Like, why would you destroy a 5090 in the current climate to prove that you can use 8-gauge wiring to power a graphics card, which anyone could have told you was easily possible. And now you know why I'm using such large gauge wiring, by the way. And just in regards to what Linus was saying, he doesn't know the exact reason why they don't use 8-gauge wiring. I can tell you why they don't use it. It's because you can't automate putting 8-gauge wires onto a graphics card PCB. When graphics cards are assembled, they use pick and place machines which automatically grab components, put them on the card. You can't automate putting an 8-gauge wire through a PCB and do that without manual labor, which obviously will cost more and things like that. And there's a lot of problems around soldering an 8-gauge wire directly through a PCB also. It is really difficult to do something like that. You could technically use those high current connectors, but they are not part of the ATX specification yet. Might change in the future. But NVIDIA can't just grab some random connector off the market and stick it on their cards when it isn't part of the standards and the whole sort of weird system that PCs use that specify what connectors are in place and other things like that. So yeah, I'm going to end this video here. I hope you got something out of this, and we'll be back with another one soon. I'm going to take a few days of a break, and then we'll come back and we'll start deep diving into some durability testing, recording, things like that. Until then, I will see you in the next video.